Hey science enthusiasts, welcome back to FactSpire, where we unpack the wildest, most fascinating mysteries of the universe. Today we're diving into something that's powered cities, sparked debates, and even shaped the course of history: the working of nuclear power reactors. These hulking machines are like the beating hearts of modern energy, turning tiny atoms into massive amounts of electricity. But how do they actually work? What's going on inside those giant cooling towers you see in the distance? And why do they inspire both awe and unease? We're about to take a deep dive into the science, the history, and the mind-blowing facts behind nuclear power. Everything from glowing fuel rods to the psychology of why we're so drawn to this tech. So grab a snack, hit that subscribe button if you haven't already, and let's power up for an epic journey into the atomic age. Now, before we get into the nuts and bolts, or should I say neutrons and bolts, let's set the scene. Nuclear power isn't just some futuristic gimmick. It's been around for decades, quietly humming away in over 30 countries. Right now, it provides about 10% of the world's electricity, and in places like France, it's more like 70%. That's a lot of juice coming from something you can't see with the naked eye. But nuclear reactors aren't magic. They're feats of engineering, physics, and a little bit of daring. They tap into the same force that fuels the stars, and today we're going to break it all down, step by step, with some surprises along the way. Ready? Let's start with the heart of the beast, the reaction that makes it all possible. Picture this: a tiny atom, smaller than a speck of dust, sitting in a reactor core. It's uranium-235, a rare flavor of uranium that's less than 1% of what you dig out of the ground. This little guy's nucleus is packed with 92 protons and 143 neutrons. But it's unstable, like a jittery tightrope walker waiting for a nudge. That nudge comes from a neutron, another subatomic particle fired at it like a cosmic bullet. When that neutron hits, the uranium atom doesn't just wobble, it splits right in half. This process, called nuclear fission, is where the magic happens. When that atom splits, it breaks into two smaller pieces, usually elements like barium and krypton, plus a handful of extra neutrons and a burst of energy. And I mean a lot of energy. One fission reaction releases about 200 million electron volts. To put that in perspective, a typical chemical reaction, like burning coal, releases maybe a few electron volts. That's a million-fold difference. Those extra neutrons zip off and smack into other uranium-235 atoms, splitting them too, and before you know it, you've got a chain reaction, a self-sustaining storm of splitting atoms, all releasing heat like a tiny sun trapped in a metal box. But here's the cool part. This isn't chaos. Engineers control it like a symphony. Inside the reactor core, a tightly packed grid of fuel rods, those uranium atoms are bundled into ceramic pellets, each about the size of your fingertip. These pellets are stacked into rods, and hundreds of rods sit in a bath of water. That water does two big jobs. It slows down the neutrons so they're more likely to hit other atoms, think of it like a cosmic speed bump, and it carries away the heat. That heat's the whole point. It turns the water into steam, which spins a turbine, which cranks a generator, and boom, electricity for your house. From a splitting atom to your light switch, all in a few steps. Now let's zoom out a bit. This whole setup happens in something called a pressurized water reactor, one of the most common designs out there. The core's sealed in a steel vessel, pressurized to keep the water liquid even at 300 degrees Celsius. That hot water flows through pipes to a separate steam generator, where it heats a second loop of water into steam without ever mixing. It's like a high-stakes game of hot potato, keeping the radioactive stuff contained. And those iconic cooling towers? They're just there to chill out the steam after it's done its job, condensing it back into water. No glowing green mist, just regular old H2O. But wait, how do they keep this chain reaction from turning into a runaway explosion? That's where control rods come in, long sticks made of materials like boron or cadmium that gobble up neutrons like Pac-Man eating dots. Drop them into the core and the reaction slows down. Pull them out and it speeds up. It's a delicate balance, monitored by computers and humans who've trained for years to keep it steady. One wrong move and you're not blowing up the planet. Modern reactors can't do that, but you could overheat the core, and that's where things get dicey. More on that later. So that's the basics. Fission heats water, steam spins turbines, and control rods keep it all in check. It's elegant, right? But this isn't some overnight invention. The road to nuclear power is paved with wild experiments, wartime secrets, and a dash of human brilliance. Let's rewind the clock and see how we got here. Let's jump back to 1938. Two German scientists, Otto Hahn and Fritz Strassmann, were bombarding uranium with neutrons in a lab, expecting it to just soak them up. Instead, they found traces of barium, way lighter than uranium. They'd split the atom, And they didn't even realize it at first. A physicist named Lise Meitner, forced to flee Nazi Germany, crunched the numbers with her nephew Otto Frisch and figured it out. Fission was real, and it released insane energy. Word spread fast, and by 1942, an Italian physicist named Enrico Fermi was ready to take it to the next level. Under a squash court at the University of Chicago, Fermi built the world's first nuclear reactor, a pile of graphite bricks, uranium, and control rods he called Chicago Pile 1. On December 2nd of that year, he pulled the rods out just enough, and the reaction went critical self-sustaining for the first time ever. No explosions, no fanfare, just a few scientists scribbling numbers as the world changed. That rickety pile proved nuclear power could work, but it was wartime, and the focus shifted fast. 3 years later, in 1945, the U.S. dropped atomic bombs on Hiroshima and Nagasaki, showing the world what fission could do. After the war, the vibe flipped. Scientists and governments saw fission's peaceful potential. In 1951, a tiny reactor in Idaho called EBR-1 lit up 4 light bulbs, the first nuclear electricity ever. By 1954, the Soviet Union fired up Obninsk, the first grid-connected nuclear plant, pumping out 5 megawatts. The U.S. followed with Shippingport in 1957, and suddenly nuclear power was a thing. Clean, efficient, and futuristic. By the 1970s, reactors were popping up everywhere, promising endless energy. But it wasn't all smooth sailing. Accidents and fears loomed large, and we'll get to that. For now, let's marvel at the tech's roots. From a lab accident to lighting cities, nuclear power's journey is a testament to curiosity and grit. But how does nature play into this? Turns out the Earth itself has been running its own reactors for billions of years. Yep, you heard that right. Believe it or not, nuclear reactors aren't just a human trick. About 2 billion years ago, in what's now Gabon, Africa, nature pulled off its own fission party. In a place called Oklo, uranium deposits in the ground hit just the right conditions. Groundwater seeped in, slowing neutrons like a reactor's water does today, and the uranium-235 started splitting. These natural reactors ran for hundreds of thousands of years, generating heat and leaving behind telltale isotopes. Proof found in the 1970s by French scientists. How'd it happen? The Earth back then had more uranium-235, about 3% of natural uranium, compared to less than 1% now, because it decays faster than its cousin uranium-238. With the right mix of water and uranium, the chain reaction kicked off underground, moderated by nature itself. It wasn't powering cavemen's huts, it just simmered away, a slow burn in the crust. Finding this was huge. It showed fission isn't some alien force, but part of our planet's story. And it's a sneak peek at how nuclear power ties into the bigger cosmic picture, which we'll explore next.